Welcome back to geometry. Quickly, we're going to cover the fundamental counting principle. If you flip through 13.3, there's a lot more there. There's permutations, there's combinations, great stuff. But we don't have time to get into that, unfortunately, so I'm just going to touch on this fundamental counting principle. The reason is because you see a lot on standardized tests, so I really think we need to touch on this, and it's very simple once you get the hang of it. So here's my first example. We're just going to do a few, well, actually, we got a few lined up here. So the homework, though, is very short. Let's say you have 3 shirts, 2 pants, 2 pair of pants, and a hat. And you're thinking about, what can you wear? I want to wear one of each. So how many options do I have? Well, here's one way to do it. This is a terrible option, but you could say, well, I could wear shirt number 1 with pant number 1 with my hat, or I could wear shirt number 1 with pant number 2 with my hat. Or I could wear shirt number 2 with pant number 1 and a hat, or shirt number 2 and pant number 2 and a hat, or finally shirt 3, pant 1, hat, or shirt 3, pant 2, hat. Just count them up, and you get 6 ways. You could dress yourself 6 ways, assuming you have to pick one of each and only one of each, no more than one. But there's got to be a better way, right? I mean, because what if you had a little more extensive wardrobe? What if you had 9 shirts and let's say 5 pair of pants and I'm trying to pick a nice number, 6 hats, let's say. This would not be so fun. This would take us a long, long time, and we'd probably make a mistake. We'd probably count one twice or forget to count one. So, do you see a shortcut here? You can just do 9 times 5 times 6. And that is 45 times 6, which is 270, or even better, that's 30. 30 times 9 is 270. There are 270 ways to pull out this outfit. Wow, that was fast. I could have redone this previous problem just by saying 3 times 2 times 1. And that would be the preference from here on. This is called the fundamental counting principle. The most common examples you'll see, and this is often on ACT, is with clothing like this. You have a certain wardrobe choice you're making, or with a menu at a restaurant. The first example in our book is about a deli, and you have sandwich, side item, and drink options. Those are very typical. I'm going to kind of take it a step beyond, and we're going to go a little bit deeper into things like passwords and things like that. And I'm going to also introduce a thing called Factorial. So let's continue. I'm going to look at the got it on page 837 in our book. It says this. I'll just kind of summarize the key points. You're creating a computer password, or automatically generating computer password. A computer is, and it has 3 characters. The first is a letter, and then followed by digits. So a number, I guess I could say, not just a number, but a digit, a single digit goes there, and a single digit goes there. And people often, now the question may be asked, can you repeat digits? Yes, you can. So you might have to think to yourself, how many letters are there? Hopefully you know this. This would be important to know. There are 26 letters in the alphabet. There are 10 digits. We count 0 to 9, 10 digits. So this is kind of like the previous problem, except you have 26 shirts, 10 pants, and 10 hats. So just like before, you can just multiply these together, which is 2,600 possible passwords. So, like the example the book gives, R38 as a password, or L55 would be a password. So we can do things like count passwords. In a similar way, let's say you have a garage code, and it's 5 digits. You may have wondered, how many possibilities are there? Well, it's just 10 times 10 times 10 times 10. It's just 10 to the 4th, or 10,000. Now, here's a little bit more clever way. Let's just actually list them out. I mean, that makes sense, hopefully. But if you were to list them, let's see. There's 1, There's 2. There's 3. Do you see a pattern here? How many would there be from 0001 to 9999? Well, of course, there's just 9,999, but I missed 000, and that makes it 10,000. So you could just count them that way too. But it's not always that easy, like this one up here with 2,600. Okay, let's ramp it up a bit. Let's say in our classroom, there are 20 desks. 20 desks in a classroom. 17 students enter. And okay, they're all going to take a seat. So if I were to, I really don't want to draw 20 desks. Maybe I can do this, it's circular. The first student comes in. How many options of places to sit do they have? Student 1. 20, right? Let's say they sit there. So student 1 had 20 options. Student 2 comes in. Assuming they can't sit with student 1, they have 19 options. Student 3 comes in, 18 options. Student 4 comes in, 17 options. And the options dwindle, right? So the very last student, if there's 17, so if they all were sitting, how many desks are available? 3, right? If all 17. So when the 17 came in, there must have been 4 available. Okay, so these are all marked up. He comes in, just the 4 in the front row. So the very last, it should have multiplication. The very last student is going to have 4 options. Let's say they go right there. So it would be 20 times 19 times 18 times 17 times 16 times 15 times 14. That's a lot of work to type in, right? You could do it. But let's imagine we up this to, what if we have 60 desks? And we have a class of 50 students. That would be 60 times 50, times 59 times 58. All the way up to the very last option would be 11, because after they take a seat, there'll be 10 empty seats, right? How would we do that? That would take a while. Well, there's a special button on your calculator. Did you know that there is a button on the calculator to solve this problem? Simpler, it is the factorial button. Now, there is another thing called the permutation. Unfortunately, we're not going to get to it. It's there in your book. Read about it and get into that. Feel free to ask me questions about it, but we are not going to cover it officially. The factorial, you've probably seen this before, is an exclamation mark in mathematics, and it means it's 5 times 3 times 2 times 1. If you want to do 8 factorial, that is 8 times 7 times 6 times 5 times 4 times. These numbers get big quick. I think the highest our calculator will go up is, I believe, 70 factorial, or 69 or 70 factorial, something like that. By the way, if you're using a TI 83 or 84, you will hit the math button and scroll left, I believe. And I think it's your 4th option down. For many of you, I don't remember, on the scientific calculator, I don't have one sitting here near me, but you'll hit, there's some PRB button, I believe, and you'll be able to get to the factorial, because you're going to need it. So is there a better way to do this problem here and this problem here? Yes, because isn't this 20 factorial, except it shouldn't have the 3, the 2, the 1, right? It's everything but the 3, the 2, the 1. So what if you just divided out the 3, 2, 1? You could put that in your calculator. This one, it's 60 factorial, but it didn't have the 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Divide that out. You can do it in just, 7 buttons, right? 6, 0 factorial divided by 10, 0 factorial. And this really leads us to the concept of permutation, but we're not going to go there. Now, just to blow your mind with a major big number, let's say that we have a big meeting to discuss this COVID-19 crisis, right? Big meeting occurs. And so we're going to get this meeting, the 50 governors of the United States, they're all going to be there. President, the vice president, that's 52. And then we're going to get the local student council. Oh, I can't spell council, can I? Local student council at Trinity Academy, and we'll say there's 16 of them, are going to join in. So these 68 people are going to put their minds together and try to solve something. So they're going to gather in a room with 68 chairs. So 68 people and 68 chairs. How many ways can they be arranged? Well, 68 factorial, which I picked this because I think this is one of the biggest your calculator can do. It is massive number. It is 2.4800, it goes on and on, but times 10 to the 96th power. That is a 97-digit number. Unfathomable. 68 people and 68 chairs. Huge. Just to give you an idea, also, with that number up here, this right here, 20 people, or 17 people and 20 chairs. What's that going to be? That number is even huge. Wow. 4.05 times 10 to the 17. Can't really fathom that. It's more than a billion. And you know, a billion seconds is about 32, 33 years, I believe. So if you were to arrange yourself every second for hundreds of years, you couldn't get 17 people. You couldn't arrange those 17 people in all the possible arrangements in a class of 20 desks. So that's just mind-blowing. I want to, another classic example I should mention is books on a shelf. Arrange 9 books on a shelf. How many ways can it be done? Well, let's see. First spot, I got 9 choices, right? 9 choices. Put one down. Next spot, I got 8 choices. Next spot, I got 7 choices. Next spot, I got 6. On and on and on, all the way down to the book on the far right. I don't really have a choice. It's just the one that's left. So another way to do that is 9 factorial. What is 9 factorial? It's a massive number, 362,880. So imagine this. Imagine you rearrange the books every day. It would take you about 1,000 years to exhaust every scenario. This is pretty close to 365,000. So, yeah, let's divide it by 365. It would take you 994.2 years to exhaust the possibilities. Now, if you were to do it multiple times a day, maybe you can get it done in your lifetime. But that would not be a very satisfying nor fulfilling life, would it? But that's a common question. The book, arranging books on a shelf. Think factorial. Okay, finally, last one. Another example is a teams. So let's say you have a 11 people on a basketball team. And you're going to set your starting lineup. Your starting lineup's going to have a center, or maybe you call him a post. It's going to have a power forward, a small forward. It's going to have a shooting guard and a point guard. So center, you look through the 11, you pick one. There's 11 choices for your center. Your power forwards, you can't have the same power forward as your center. So you have 10 options for the power forwards. You have 9 for the small forward. You have 8 and you have 7. Of course, it doesn't matter the order you pick them. If you pick point guard first, it doesn't matter. So how can you do this? Of course, you can multiply those numbers out, but you could also say 11 factorial divided by 6 factorial, because we didn't want the 6 factorial. In this case, it probably would be easier to do 11 times 10 times 9 times 8 times 7. You could check it both ways to make sure you're getting the right answer. It should be 55,440 ways. So if you know your friend says, hey, just hang in there, you know, sure you're not starting at point guard, but he mixes the lineups up a little bit. Eventually you'll start. Well, there's over 55,000 ways, so it may take, it may be more than just the number of games you have this year. But there you go. So this is a way of counting. So we are learning how to count big numbers. You can use this this is really necessary in probabilities. Like if you're counting different types of hands you can get in a card game. If you want to calculate probabilities of getting certain types of hands, the numbers are so big, you need these kind of counting techniques. Like I say, really, we're right on the